Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020. And the topic of this lecture is Cauchy Euler equation. With the same relative ease that we were able to find explicit solutions of higher order linear differential equations with constant coefficients, it really doesn't carry over when we have linear equations with variable coefficients. We shall see in chapter 6 that when a linear differential equation has variable coefficients, the best we can usually hope for is to find a solution in the form of an infinite series, or perhaps a truncated infinite series. However, the type of differential equation that we consider in this section is an exception to this rule. It is a linear equation with variable coefficients whose general solution can always be expressed in terms of powers of x, sines, cosines, and logarithm functions. Moreover, its method of solution is quite similar to that for constant coefficient equations in which an auxiliary equation must be solved. For that reason, Zill, in later editions of his books, included it in chapter 4, and I am making it follow in the same footsteps. So, a Cauchy Euler equation is a linear differential equation of this form. And it can be homogeneous or non-homogeneous. Now, the observable characteristic is that we have a constant times x to the nth power, and that's the nth derivative. So these match. Here we have x to the n minus 1, and that's the n minus first derivative. So you see those always match. That makes this a Cauchy Euler equation. And we're going to start, as we did in previous sections, by looking at the homogeneous equation. And the solution of higher order equations follow analogously because we will have polynomials. Also, we can solve the non-homogeneous by variation of parameters once we have determined the complementary function y sub c. Annihilators don't work because they only work with constant coefficients, not variable coefficients. Now note that the coefficient ax squared of y sub double prime, when we're talking about the second order equation, is 0 at x equals 0. So we have to avoid x equals 0. For the first part, we're going to talk about from 0 to infinity, but we'll talk about what happens if you go to negative. So the real thing is we have to avoid x is equal to 0. So here is our method of solution. We're going to try a solution of the form y equals x to the m, and m is to be determined. So we plug it in and we see what happened. Now notice whenever you take the kth derivative of y, then you will have all of these constants times x to the m minus k, but then we take that times x to the k, so this really becomes just a bunch of numbers times x to the m. So as an example, let's look at the second order differential equation. So we have this. When we take two derivatives, we're going to have m times m minus 1 times x to the m minus 2. But then we're taking that times x squared. That makes that x to the m. Plus, here you're taking one derivative is m times x to the m minus 1, but then I'm taking it times x. So that becomes this, bm x to the m. And here is just c times y, which is c times x to the m. Now, there's an x to the m everywhere, so we can factor it out. That's not equal to 0. That means the only way this can be equal to 0 for the homogeneous equation is for this polynomial to be 0. We're going to call that the auxiliary equation. This is what it is. Or when we simplify it, we get this. Now, as before, there are three cases that we need to consider, depending on whether the roots are real and distinct, real and equal, or complex roots. In the last case, the roots, of course, appear as conjugate conjugates, one with another. Let's look at case 1 then, where we're saying, suppose the polynomial is such that we have real distinct roots. So m1 and m2 denote the real roots of the equation, and m1 does not equal m2. Then these are a fundamental set of solutions. So the general solution is going to be a linear combination of the two. So here's a problem. Solve this IVP. And in fact, it is an initial value problem. You know what to do. And when we come back in 20.1, we'll see how you do. See you.